In this video, we're going to look at function composition, what it means and how it works, and how it can be written in a few different types of notation. So first, you have to understand that function composition is about layering functions on top of one another. Okay? And this operation or this idea becomes important when you have more than one transformation that need to be applied to an input kind of in sequence. So a physical example might be something like an assembly line. Okay? In an assembly line, if you're building, say you're building a car, you want to start by taking the input, which would be all the materials for the car, and you need to put them together, but the order in which you put them together really matters. If you try to put the wheels on the car before the axles are on the car, the wheels are just going to fall down. If you try to put the windows in the car before the frame has been constructed, then the windows are going to fall and the thing is going to break. So the order in which you put them together really matters. So with function composition, what we do is we kind of insert one function inside another. And what that does is it creates a sequence of transformations. You take the input of the very, very first function, then that gets altered by the function, turns into an output, and then that gets fed to the next function. So function composition, when we write it down, looks like putting things inside one another. But if we think about it in a more physical sense, what happens is one function happens, then the next function happens, and it really creates a sequence of functions. Okay? For notation, function composition is written in two really common ways. The first one that I'm going to show you is a special notation for a composition, and it's not really that useful because it doesn't tell us how to do it. The second is how function composition appears using argument notation, which is a little bit more useful because it kind of gives you directions on how the composition works. So if you see a little circle, okay, that is function composition. And you could read this as the function f composed with g. Okay? So that's a little piece of notation that you might see in different situations, and it stands for function composition. Now, if I'm trying to tell you what this means, I need to use argument notation. And the really important thing to understand here is even though we read this set of symbols left to right, argument notation is going to show us that it really happens right to left, or inside to outside. And I'll show you what I mean in just a second. So if I write a function composition in argument notation, what I mean by this is f with g put inside it, and then let's make x our input argument, follow standard convention. We'll put x into g. Okay? So f composed with g means to take the g of x and put it inside f of x. If I wanted to figure out what this composition was doing, I would take the x, substitute it into g, figure out what the output of g was, and then feed that into f. Okay? So let's work with some formulaic examples to see how this behaves. Let's keep it relatively simple, and then look at the effect of two different functions. So let's try to choose maybe f of x. F with x as an input would look like x squared. And I'm going to overload my notation here. I'm going to reuse x, and it's going to mean different things in different contexts. So here, I'm giving you a definition for the output values of f. I'm giving you this formula, x squared, which tells us what f is doing. F is a squaring function. And I'm going to use maybe g of x. Okay? And I'll define that as, how about x plus 1 divided by 2. Just make it relatively simple. Okay, so there's the function for g of x. So both of these lines, I'm defining how to take the input of x to the function g and produce the output. How to take the input of x to f and produce the output. If we look at the composition, f composed with g, then what I want to do is I want to take this g and I want to put it inside f. So let's write another formula for f where we don't use x as notation. So get this idea of altering the argument of the function and seeing what happens to it. So if f of x is equal to x squared, f of t would be t squared. Okay? F of z would be z squared, and f of 2 would be 4. 2 times 2, 2 squared is 4. Okay, so just get that idea of flexibly changing what you're putting inside f. All right? And now, following that sequence of ideas, I want to do this. I want to put g of x inside this function f. Okay? So, f of g of x is going to be equal to g of x squared. Okay, it's exactly the same pattern that we were following over here, just changing what that argument is. Except now we can even replace the g of x with its formula. So we could say that f of g of x is equal to x plus 1 over 2 squared. This is the composition of f with g of x. Okay? So that's how you would define a composition. If you wanted to know the value of f of g of 2, you can now just plug 2 in here and work out the algebra, work out the arithmetic to figure out the value. Something that's important to understand about function composition, I said it earlier, kind of informally, I said the order really matters. The way you do things, the way you put things together has an impact on what comes out. That's especially true with function composition. So here we've done f composed with g and we've put the g inside of f. This is the result. Okay? Next, I'd like to switch the order there. I'd like to know what happens if I put f inside of g. Right? So you have to think about these functions as transformations that as we define them, we put x in as the input argument, but really what I want you to capture, what I want you to hold on to is this idea of altering the input argument in certain ways. That's the function that we want to start to use. So f composed with g came out like this. Watch what happens if we go in the other direction. I'm going to do g composed with f. And I'm going to use x as my input argument to f. Okay? So, same idea that we were using here. I'm going to take my g and I'm going to replace the input x with f of x. Okay? So g of f of x should look like f of x plus 1 over 2. And I have a formula for f of x, so I can use that. And this looks like x squared plus 1 over 2. Okay? So that would be the composition g composed with f. If I use this notation, looks like g, little circle, f, and if I want to link that to argument notation, I can actually put an argument on the end there. Okay? And now, the really important point here, the real key point here, is these two things are not the same in general. So, function composition is not commutative. The order in which you layer things matters. These things can't pass through one another without changing what's happening to the output. Right? If you want to see that, just look at this. Just multiply this out. This bottom term, if I distribute the 1/2, is 1/2 x squared plus 1/2. This first term, I have a binomial in the numerator, which I would have to multiply out more carefully, FOIL that out if you want. And I also have this 2 squared in the denominator. If I work all this stuff out, the numerator multiplies out to give x squared plus 2x plus 1, and the denominator squared gives us 4. Okay? So if we take one more step and we distribute that division by 4 at all the terms, we get x squared times 1/4, x divided by 2 plus 1/4. And these are different quadratics. This little mark is just a mark on the board, it's not a minus sign. Okay? So we have 1/4 x squared plus x over 2 plus 1/4, and down here we have 1/2 x squared plus 1/2. The constants are different, the coefficients of x squared are different, and one term has, one of these functions, one of these compositions has a linear term in x over 2, and the other one doesn't have that at all. So these are completely different. And that's true in general, that the order matters when we do function composition. Okay? So that's a basic idea behind function composition, how to build compositions by putting one function inside another, and the property that function composition is not commutative. The order really matters when you build these things. Okay?